And it's a good org. And historically, a lot of people who take this class join the org and vice versa, so it's a good cross-promotion there. All right. Also, this is a good segue because today we're going to be talking about signal processing, which is a very rich field. Professors always joke that whenever they bring anything up related to signal processing, it's like, oh, you could get a whole degree in this, or you could get a whole PhD in this, and that is unbelievably true. So this is a very, very dense set of topics, and I'm only going to be able to really scratch the surface. So for anyone who has more knowledge, please be patient, because a lot of people do not. So yeah, broadly we're going to be focusing on processing for EEG data, but these general things are true for most time series data and time series neurological data in particular, especially, IEEG or ECOGs, MEG, EEG. It's all roughly the same in terms of the basics. So this is a figure that we showed from last lecture, and again we have this general set of what's happening when we're doing an EEG experiment. So we have our participant who's connected to a cap. They are seeing some sort of monitor that has events happening. Maybe they're responding. That computer and monitor is sending some codes to the amplifier. But what's really happening after the digitization? So in this box it says filters and amplifiers. This is assuming hardware filters. Nowadays it's very uncommon to use hardware filters for EEG processing. You're going to have one initial filter that is sort of a digitization filter, which is a low-pass filter, which I'll talk about. But most of our signal processing is done after the computer has digitized the signal. And this is because it tends to be cheaper and more reliable to create digital filters. And you can change them after the fact rather than having to be hard locked on a set of filters at recording time. Before that, it's good to talk about what types of BCIs we might be creating and why we might need to process them and why they would need to be processed differently. Broadly speaking, there are two different categories of BCIs. We have synchronous, which are things that you can think of synchronous as being event locked. So you know when certain events occur. Let's say you know when a user has pushed a button or has started looking at something or has heard a sound, and you are expecting some signal of interest to occur a certain amount of time before or after that stimulus. So in this case, if we're looking at event-related potentials, let's say we're looking for the P300, which I'll talk about later, we would expect to see some sort of activity between 300 and 800 milliseconds after a task-relevant event occurs. So this could be seeing, if you're doing a speller, this could be seeing your target letter flash up on the screen. So the synchronous BCI knows when things happen, and they might actually know what has occurred, but that's not always necessary. An asynchronous BCI is something that is much more difficult. It's something that is sort of constantly looking for a signal. And the way to explain this that Professor Desai usually uses is explaining it as sort of your Hey Siri command. And if I just triggered someone's Siri, I'm sorry. But what's happening is that your phone is constantly looking for this very specific message, and once it recognizes it, it does some action. As you can imagine, this could be pretty hard to do with neurological signals. It's not as clear as, there's not really this Hey Siri signal in the brain. Even some of our better signals, such as, foot versus tongue motor imagery or something, are still going to be similar enough that you might get false positives or false negatives all of the time. This is sort of what you would want for an ideal neuroprosthesis. So you'd want to be able to have a system that's constantly and asynchronously looking for commands to, rotate the arm or clench the hand, something like this. But it is a much harder problem to solve. And for the sake of convenience, I'm going to focus on things that are mostly from a synchronous perspective, but a lot of these things can still apply to an asynchronous BCI. And this is the overview of standard pre-processing for EEG data. Obviously, you have to acquire the data. This can be either something that you're acquiring in real time, which we'd call online, or this could be loading some offline data that you collected previously. We then filter the data. This can be temporal or spatial filtering, or both. We remove artifacts. Common artifacts include, the electrodes moving around from people walking around, or even from talking or clenching their jaws. eye blinks are a huge artifact. Sometimes they're a signal. We then do this thing called binning, or what a lot of people in the field call epoching. And yes, I know there are many, many ways to pronounce this word, epoching, but most of us say epoch. It's just sort of the standard. So you can use it as a noun or a verb. You can epoch data, or you can look at epochs. And this is essentially just extracting data relative to a certain event. Again, we're focusing on synchronous data. And then we baseline correct, and I'll talk about this later. This is a general set of tips. This is a very common set of things you would do to pre-process any EEG data or neural time series data. But again, it's not exhaustive, and today we're mostly going to be focusing on filtering the data. It's also important to realize that all of these steps are somewhat interchangeable, depending on what you're doing, and you might do some of them multiple times. So you might epoch the data first and then filter them. You might remove artifacts first and then filter them, depending on what type of artifact removal you're using. You might do multiple baseline corrections or no baseline correction, depending on your modality. So although I lay it out in this very structured, this is how you should do it, all of these steps can be done multiple times or in different orders, and it's sort of just up to what the task is to know what's right. And after we do all this, we're going to be doing something, right? We're not just going to be doing this. We'll either be plotting the data, we'll be using it for classification, we'll be using it for statistics. So this is the first step of a long chain. And one general tip is to visualize your data often. So plot your raw signals, make sure that your channels look like actual neurological data and not just noise. After you filter your data, make sure that they're not completely distorted, make sure that it looks like the filter was operating correctly. When you're removing artifacts, make sure that those artifacts are gone. You can use your eyes a lot. They're very useful. Okay, so briefly, let's talk about some things that you might want to pay attention to when you're working with offline data. So this is data that has already been recorded. You could have recorded it, or it could have been something you found on the internet. In general, you're going to have to load your data. This sounds like it'd be trivial, but not all data sets are formatted the same way. This is where the strength of a library or toolbox really starts to shine. So MNE and EEG Lab both have a lot of code for loading in different modalities. So if you're recording something using any popular amplifier, let's say you're using the Brain Vision ActiChamp, which is what I use, or you're using a Biosemi, it's going to save it into a format that the big toolboxes know how to open. But if you're working with some custom amplifier or some lesser known brand or some older equipment, it might just save it into some text document or a set of different CSV files or whatever. And you're sort of on your own most of the time with that, and you have to format and load the data. And when you're doing it with these non-standard data, you really want to make sure you're reading the description very carefully, because it tends to tell you what you need to know. But this is somewhat obvious, but it's good to mention, because especially once you get confident or cocky, you can think that you know a lot more than you do and mess something up and everything is wrong. But for most EEG data, there are some very key pieces of information. The channel locations, so this is where on the head the electrodes are. So if we refer to this figure, this is the 1020 system. It's not the only system, but it's the most common. So you need to know, maybe this is electrode 1, 2, 3, 4, 5, 6, or maybe it's, 1, 2, 3, 4, 5, 6. Whatever it is, you can never assume you know which channel number refers to which location. You have to have that information given to you. So that'll be in the description, or it'll just be in the metadata. You also need to know the sampling rate. This is essentially how frequently the analog signal that is our EEG data is being sampled and digitized. And this is very relevant not only for plotting to make sure that you're getting your time points in the right places, but for designing filters. So the sampling rate is critical for filtering your data. Event labels are essentially which event has occurred. So let's say you're showing people certain images and they're also responding preferentially to some of those images. You need to know if an event was them seeing an image or them clicking, and you need to know which image or which click it was. Was it correct? Was it incorrect? Was the image red? Was it blue? Things like that. And the event times are when these events happened. And typically, this is going to be synchronized with your EEG time events, or you should do everything you can to get them synchronized to that, because you want to make sure that you're looking at the data as close as possible to when the event actually occurred most of the time. Or you want to be off by a certain distance. So maybe you want to look 300 milliseconds after a stimulus occurred or a response occurred. But you need to know precisely when that happened in order to do that accurately. And then acquiring data online is a whole nother kettle of fish. It's pretty hard if you're working with some non-standard data, but you need the same amount of critical information, so you still need to know event labels, when they occur, you need to know the sampling rate, channel locations. When you're working online, you typically need a buffer. This is because of baseline correction, which I'll talk about right after this. But we often want activity prior to a stimulus that sort of has no information, this baseline activity, which is just the brain doing its thing. And we want to take the average of that baseline activity and subtract it out from our main signal in order to zero everything. And I have a figure for this that'll make it more obvious. When you're implementing a buffer and you're using something like, if you're using Python or any modern language, you want to use a queue, which allows you to, you're always going to want to be getting rid of the oldest sample and adding a new sample in, and a queue is optimal for that. In Python, the best solution for that is a double-ended queue in the collections library. It's very, very efficient. And that's what I use for my BCIs, as I use a deck. So yeah, this can be difficult to do with non-standard protocols, like if you're just recording from an ADC directly, like let's say you have created an amplifier using a TNC or a Raspberry Pi Pico or something like this. You're going to have to use whatever communication protocol you have and synchronize the timestamps, so you're sort of on your own. You're in the Wild West. What's a lot easier is if you use something that there's already a lot of support for. In this case, the thing I use the most and a lot of BCI researchers use is the lab streaming layer. Everyone calls it LSL. This was also developed here at UCSD at the Schwartz Center. Same people that made EEG Lab and BCI Lab. And this is something that most manufacturers have supported now because it's very popular. So OpenBCI has support for that. The Brain Vision ActiChamp has support for that. Biosemi, the wearable sensing has it. And what's nice about this is if you write your code to accept an LSL stream, you don't really care what the manufacturer is. Everything is written to accept an LSL stream, so you can have your code work, your BCI work with any manufacturer's equipment, as long as it outputs LSL. So this is a very popular and a very reliable choice. And some manufacturers make their own protocols. Usually they're based off of UDP or OSC, which is the Open Sound Control protocol. I don't know. I know Super Collider uses that. Anybody use Super Collider here? Music synthesis software. It's cool. And then event synchronization must be checked. So even if LSL sends you an event marker and an event time, there's going to be some delay between when that event is actually sent to the machine and when LSL sends that event marker. So you want to synchronize these. If it's a visual stimulus, I use a photosensor, which I'll talk about later in the corridor. And if it's an auditory stimulus, you can use a microphone. And these are sensors that are sent straight to the amplifier that are recording the physical properties of the stimulus, so you can use them for synchronization. All right, so let's talk about some filtering problems. This is I think we've all seen something like this, or maybe this exact GIF, where we have a video camera recording something. In this case, it's a helicopter. And to our eyes, because of the way that the video camera is sampling the helicopter, it appears that the propeller is not moving at all. It's sort of just stationary, or maybe it's slightly moving. And this is a thing, people call this particular effect the wagon wheel effect, but it's an example of what we call aliasing. So here's another example, but aliasing essentially comes from undersampling a signal. So if you have a signal that is a very fast frequency and you sample fewer and fewer points, rather than getting a true representation of the signal, you're going to end up creating an artifactual signal that is at a much lower sampling rate, as we see with this GIF. So although we have this oscillation at this particular frequency, as we start sampling lower and lower, we might see these artifactual slow waves and oscillations. So those don't actually exist in the signal, but because of poor sampling, we see them. That's aliasing. And more formally, it's defined by the Nyquist or the Nyquist-Shannon theorem. And the critical thing to know is that you need to sample at 2 times your maximum frequency. So with EEG, we're typically not interested in any signals above, honestly, above 60 hertz is very uncommon, but typically we're not interested in anything above 100 hertz. So sampling at 250 hertz, for example, is totally sufficient to capture all of the relevant data that we have in EEG. And the brain isn't really producing high amplitude signals or signals of amplitude that we can even measure with most amplifiers at those frequency rates. Like there's pretty much no, okay, well, depends who you ask, but there's not really that much relevant EEG activity higher than 100 hertz. There are some people that will record the 4 kilohertz brainstem response, and so they need significantly faster sampling rates. But for most of EEG, you could get away with, 250 hertz sampling. But again, really depends on your application. So, and by the way, like always, if you have questions, just ask her in chat, just pop them in chat. Baseline correction is sort of showcased very well in this picture right here. So we have the uncorrected signal. We can see that the activity is slightly higher than 0, and this drift is caused by just real-world things. So when you're recording from a participant, there's going to be this drift that you see in the EEG signal over time. That's going to be caused by differences in skin hydration, sweating, movement, just temperature. The electrodes are just going to drift. And we try to correct for this by applying some filters, but even with filters that remove this linear trend or this DC offset, as we call it, you might still see variation in your individual trials when you epoch them. And what baseline correction does is it allows us to put all of our trials into the same zero-centered area. So in this case, this baseline activity, it looks like it's a good baseline in the sense that there's not really any prominent neurological activity. And so what we can do is we can define this window from negative 200 to 0 milliseconds. We can compute the average of that, and we can subtract that average from every single time point, which then gives us our baseline corrected signal. Now, it's very important to choose a good baseline, because if your baseline is bad and contains some sort of neurological information, let's say we instead chose our baseline to be from 0 to 200, we would be influenced by this ERP component, the P2, and it would shift our entire signal. So choosing a good baseline and designing your experiments to have a good baseline is a non-trivial and very important part of EEG research, specifically ERP research. But baseline activity is also very important for doing things like time frequency analysis. So it's not just ERPs, it's a lot of different types of experimentation. And so yeah, this is the baseline window. Okay, so once you've baseline corrected the data, you'll typically apply some sort of filters to it. Again, you can filter before, but you can filter after. And there are 2 broad categories of filters, which are going to be low-pass filters and high-pass filters. And I know when I was first learning about filters, when I was doing audio processing, I would always get confused between the 2, but just read it literally. A low-pass filter passes low signals. A high-pass filter passes high signals. And the low and high in this case is just frequency. So low is slow and high is fast. So let's look at an example of that. Here is a generated signal, and this is a simple sum of sine waves. So in this case, we have a sum of 5 hertz, 10 hertz, 30 hertz, and 60 hertz. And as we can see, the sum of the signal looks pretty complex, it looks pretty intense, but it really is just a simple sum of sine waves. Now we can simulate a low-pass filter. So in this case, we've created some hypothetical filter that is, let's say it's a 6 hertz low-pass filter. So we're going to only let things that are slower than 6 hertz pass, and everything else that's faster than 6 hertz is going to get blocked out. So because we have the only thing slower in our signal that we have than 6 hertz is 5 hertz, we're left with this nice 5 hertz oscillation. And I want to make it clear that I haven't actually filtered the data in this case. This is a simulation of what a filter might do. I'll actually show you some filter data in a second. Here's a different example where we change the low pass. Let's say in this case we have a 11 hertz low pass. So now we're saving 10 hertz because it's slower than 11 hertz, but we are also saving the 5 hertz, right? Because it also fits that check. So we're saying anything slower than 11 hertz, you're good to go. So 5 and 10 hertz come through. And then we also have the high-pass filter. So in this case, we have our fastest frequency is 60 hertz. And typically, this is going to be an artifact. Actually, so depending on where you are in the world, we have a different voltage and different frequency of our main line, right? So the things that we're plugging everything into in our outlets, the main current here in the US is 60 hertz. In other places in the world, it's 50 hertz. Some places it's 40 hertz, I believe. But here, our line noise is 60 hertz. So typically, when you see a 60 hertz signal in our EEG data, which is also an alternating current, it's an artifact, and we want to remove it. And the way that you can do that is by, for example, if you're really only interested in signals from, let's say, 0.1 to 30 hertz, which is a very common range, a lot of the times you could just apply a pretty aggressive filter from 0.1 to 30 hertz, and the 60 hertz noise kind of goes away. But sometimes you might need to specifically target it because the noise is so gigantic. And really, when you record bad EEG data that has these line noise artifacts, it's very obvious to tell. So it's not typically subtle. But in this example, let's just say that we really want to isolate the 60 hertz noise. Maybe we want to make sure that it is line noise and not some sort of crazy neurological signal we've never recorded before. We would use a high-pass filter. So let's say in this case, we'd filter everything higher than 59 hertz. And since the only thing we have faster than 59 is 60, that's all we keep. Now, using these two filters, the low-pass and high-pass, we can also create two different types of filters, which are the bandpass filter, which, again, read it literally. It'll pass a band of frequencies. That 0.1 to 30 hertz thing that I mentioned is an example of that. And then we have the opposite of the bandpass filter, which is the band stop or the notch filter. And the reason it's called the notch is because it's sort of, if you look at a straight line and then you have a little bit of a notch in it, if you look at the frequency response function. One sec, grab water. So yeah, typically we'll call them notch filters and not band stop, but they are technically called band stop filters. So here's an example of a simple bandpass filter. In this case, we would create a filter that's, let's say, from 15 to 40 hertz. So we're only going to keep the signals that are faster than or equal to 15 hertz and slower than or equal to 40 hertz. And in this case, in our example signal, the only thing that meets that is 30 hertz, so we keep that in there. And then here's an example of a notch filter. So in this case, let's say we're notching everything from 6 to 59 hertz, which means that we're only going to keep the things that are slower or faster, so slower than 6 hertz, faster than 59 hertz, which only gives us our 5 and 60 hertz. So again, this stuff can be pretty confusing if you let yourself get confused by it, but if you just literally read what the filters are doing and think about it, it can become easy, and you can always refer back to these examples, and yeah. And if anybody has any music production background, the filters are exactly the same. So if you've applied a low-pass filter to your audio track, you'll hear that it becomes a lot darker, a lot more muffled. And if you apply a high-pass filter, you only hear the audio and the hi-hats and maybe the harmonics of your instruments and stuff. The exact same concepts are true with this. And in fact, I like to joke about how, in a lot of ways, EEG signal processing is cheaper and easier than audio processing, right? We're sampling our data at, on average, 500 hertz. Audio is sampled at 44 kilohertz, way faster. The filters are way more aggressive. But of course, because we have slower oscillations, we're also limited to a lower order set of filters. And anyway, in terms of raw computation, it can be a lot more efficient than processing audio, but in reality, they're both very complex and very different fields. But if you've ever tried to create your own audio processing or your own EEG processing toolbox and you try to do the other one, you'll find that you're creating a lot of the same functionality. Okay, so I know I said that there are some types of filters, the low pass and high pass and stuff. There's another set of types of filters. In this case, we have FIR, or finite impulse response, and IIR, infinite impulse response. You could very legitimately take entire years where you focus on just a single one of these types of filters, and we really don't have the time for that. So I'll just give you the bullet points of the features that are relevant for us. So FIR filters are stable. They have a linear phase shift, which means when you apply a filter, the signal is going to be temporally shifted by a linear amount. And a good example for that is the windowed sinc filter, which you can find in MATLAB, you can find it in Python. IIR filters are unstable. You have to be very careful when designing them. They have a non-linear phase shift, which means that different parts of your signal are going to be shifted in time differently than each other. So it's not a simple linear correction, but some frequencies are going to be moved more than others. And a very common example for that is a Butterworth filter. So when I say unstable, this is sort of a loaded thing. IIR filters can be designed to be stable, so you have to sort of just check their parameters. A lot of the times people use Butterworth filters in EEG processing still. Typically second or fourth order Butterworth filters they're not uncommon, but it's very important to check their use case with your data, because even if they're stable in one person's use case, it does not necessarily mean they'll be stable in yours. This is very dependent on the parameters that you're using. So if it's a bandpass filter, the low cutoff and the high cutoff are critical for stability. The sampling rate can affect it. So in general, I'd like to focus on using FIR filters, which perform generally a lot more reliably. And they have a lot of really nice properties that make them intuitive for working with. And again, many filters can be used, and it's important to make sure it's valid for your purpose. Also, I don't know if I said it, but I think it was on a slide, but we're focusing just on temporal filtering today. We'll cover spatial filtering when we talk about motor imagery and common spatial patterns. So the key information for our filters is similar to the things that we need to know for our data, but different. The sampling rate is critical. We need to know the digitization, the sampling rate of our data. We also need to define a frequency cutoff. So this is going to be at which point we decide to start passing things lower or higher. Or if we're using a bandpass or a stop band, it'll be a set of two values. So it'll be, an array of frequencies we're going to allow. And then the type of filter, low, high, band stop, and the size that we want our filter to be. So this is going to be essentially the number of coefficients that our filter has. There are different things happen depending on the size of the filter. So even if you're designing the same filter, but you're changing the order, which is what you'd call it with an IIR filter, or you change the number of taps or the number of coefficients in an FIR filter, it has different effects on the data, which we'll explore. But yes, when in doubt, check the literature. So there's almost a 0% chance you're doing something that nobody has done before. You're probably building off of something that people did in the past. And unless you are specifically researching the effects of filters and you already know all of what you should be doing, you should just see what other people have done, see what the consensus is. There's a lot of people that criticize filtering and stuff, so listen to those people, follow the best practices for your field, and always visualize your data before and after filtering. It's a very cheap and easy thing to do, and it's a good way to catch simple mistakes. Like you might have accidentally, maybe you wanted to do a low-pass filter, but you forgot to change the variable name, and it's doing a high-pass filter. You would instantaneously be able to tell that in your data. Or maybe you have a two-dimensional data set where you have channels in one dimension and time on the other dimension, and you accidentally filtered across channels rather than time. Again, you'll instantly be able to see that. And these sound silly, but it happens. Like I have done that when I've been making things. I'm like, why is my stuff not working? And then I plot it, I'm like, oh, I filtered across channels, not across time. So just all you have to, simple solution, just plot your data. You'll easily be able to fix those problems. So yeah, size is something we're going to explore right now. Here's another simple raw signal. I just gave this 10 random points. And now we're going to create the simplest possible filter. So what this filter is going to do is I'm going to give it a number of points, and I want to take those points. Let's say I'm going to take 2 points, and I'm going to compute the average, and I'm going to return that signal. So that's the simplest filter I could think of right now. So right here, you'll see that this data point is 0. This is because I 0-padded the data, because otherwise we'd run out of signals. But essentially all this, it's doing exactly what I said. So we're taking 2 of the points, we're taking the average, and we're returning that. Then we move on to the next one, take the average of that, return it, average, so on and so forth. So as we can see with 2 points, the signal is almost exactly the same. It's not really that aggressive, and we can almost see that it looks like the same signal, but it's just been shifted a little bit. It's been a little delayed temporally. So this peak corresponds to this peak, this one to this one, this one to this one. Same with the troughs. So what happens when we make this more aggressive? So here's a 4-point filter. It's becoming a little smoother, right? As we saw in this one, it's still pretty sharp, pretty jagged, but now the peaks are sort of starting to level out. And then we can add, double this again and make an 8-point filter. And again, the difference is pretty noticeable. The signal is a lot smoother. And all we've done is just change the number of points that we're using. We've changed the coefficient, or we've changed the filter order. And so I do have a question, which is, what type of filter is this? And the options are low pass or high pass. So go ahead and sign on to class question. I'll give you guys a little bit of time. Oh, it's okay. I really hate the UI for this. Okay, the question is live now. Yes, what type of filter is this? Low pass or high pass filter? And you can just think about this transition. And I should also mention that this is the first question I've had where there is technically a correct answer, but whether or not you get the answer right doesn't matter for your participation grade. So feel free to just take your best guess. I'll just flip through these as like a little mini animation. So now there are 52 people on Zoom, so I'm going to wait for at least 52, and there's about 30 people in here, so should expect somewhere around 80 responses, and then I'll stop. And again, it's okay if you get it wrong. I see 70. I'll let this run for a while, but I'll move on. I do want people to be able to answer it. But I'll give you the answer, and once I see the total answers around 80-ish. So let's look at a real-world example now where I actually filter the data. So in this case, I am creating an FIR filter with these relevant parameters. So the sampling rate, which is the same as the data, is 1,000 hertz. The filter that I'm using is a low-pass filter. The cutoff is 50 hertz because my goal is to get rid of my 60 hertz signal. I have 31 coefficients, which is the size of the filter. The filter is causal, which I'll talk about in a bit, and it has a linear phase shift, which is what I mentioned in terms of the signals being moved temporally. So as you can see, the signal looks almost exactly the same. It's not a very aggressive filter, so we still see that 60 hertz noise, but we see that all of the peaks and troughs have been moved a little bit. Let's look at the same filter, except now all we've done is we've changed the number of coefficients. So we went from 31 to 101, and as we can see, that signal has shifted even more in time, but it's still not aggressive enough to get rid of that 60 hertz noise. And we can also see that the amplitude of the peaks and the troughs have increased a little bit. And now let's do it once again, and, okay, maybe I have it in a different example. So let's do a different filter this time to make the change more obvious. We're going to get rid of our 20 hertz signal. We're going to create a 20 hertz low pass, So now we're going to try to isolate our 5 and 10 hertz. And we're going back to 31 taps. And we do the same thing to 101. And now we're seeing a true difference. So although we're seeing the same shift to further in time, we're now actually isolating our signal of interest. And if we do that again and go to 301, we're really isolating that 5 and 10 hertz. So we can see that transition. It's sort of spiky, a little irregular, and now we're getting that true 10 plus 5 hertz sine wave. Now, one way that we can fix that temporal shift is by using a non-causal filter. So the only thing different between these two filters is that we've applied a non-causal filter. And in this case, the only thing we need to do with an FIR filter is to literally shift the signals over in time. But the more common way of creating a general non-causal filter is by using something called filt-filt, which means you filter the signals one way, and then you filter them the other way in time. So briefly, this is the different types of filters that we have. A causal filter only uses data from the past, and this is something you can do in real time. A non-causal filter uses data from the past and the future. So in this case, this would be taking all of your data points, filtering them one way, taking all those data points, filtering them the other way. You'd still need all of the signals in order to be able to do that. And an anti-causal or acausal filter uses it in the reverse, which is not really typical. Okay, and let me end the question and give you the answer was that it's a low pass filter. Which let's see how many people got that. Really wish I could just see the. Okay. So most people got it right, low pass filter, and the way that essentially the giveaway is that it is sort of smoothing these higher frequency changes. The peaks and the troughs are becoming attenuated, they're becoming smoother. That's a typical effect of a low pass filter. And in general, any averaging is a low pass filter. So whenever you take the average of any number of points, you are effectively computing a low pass. So that's all we have for today. We'll talk some more about filtering on Friday, and we'll also do some live coding. The assignments are going to be released on Friday because our environment is working. So if you're having problems with that, email ETS. I can't do anything to help you. All right.